Okay. Welcome to our N3AS Seminar. Today we are very pleased to have Professor Mauricio Bustamante from Niels Bohr Institute, Copenhagen. He will talk about cosmic neutrinos, high energy cosmic neutrinos. Over to you, Mauricio.
Thank you very much, Anupam. Thank you, everybody who's here tonight, or today, rather. It's always nice to talk to the other side of the world from my living room. So thank you for that. Yes, I'm going to talk about neutrinos, but let me take a step back and first look at the big picture. And the big picture is that we're trying to do astroparticle physics. And for that, we want to look at sometimes the highest energies and at these kind of beasts, cosmic accelerators whose nature is still unclear, but they are most likely sites where protons can be taken to energies to 10 to the 20 or 10 to the 21 electron volts. They are not clean like our accelerators, so they make secondary particles, and that means cosmic rays, photons, gamma rays rather, and neutrinos. And it is neutrinos that are going to be the subject of today's talk, and in particular, one specific property of neutrinos that is not shared by cosmic rays and gamma rays, and that is flavor. Now, the full picture of the high energy universe is given by studying not just neutrinos, but also cosmic rays and photons, and we'll see in a bit that their origin is most likely connected. I should also mention gravitational waves. But today, let me be a bit selfish and just focus on neutrinos and why their special property of having flavor gives us insight that is not necessarily given by the other messengers. Very well. So which neutrinos am I talking about, and why are they interesting to do both high energy astrophysics and high energy particle physics, especially with flavor, but not just with flavor? Let me make that clear here. And in a plot of neutrino energy in the x-axis and distance traveled by the neutrinos from their sources to the detectors in the y-axis, the neutrinos that we have been learning from for decades at this point are more or less in the lower left corner of the plot. So you have here short basin neutrinos, solar neutrinos, reactor, atmospheric, and supernova neutrinos have a longer baseline, so they're up here. But the ones that I want to talk about today are the ones on the opposite corner, the high energy neutrinos, which go roughly from TeV to, let's say, 100 PeV or so in energies, and ultra high energy neutrinos, which go above that, 100 PeV and beyond. And we have seen high energy neutrinos. We have not seen ultra high energy neutrinos. We hope to see them, and I will say more about that later. But both of them, this is of course a kind of like a blurry line distinguishing between them, but these high energy neutrinos have two, let's say, essential reasons why they are interesting as probes of high energy astrophysics and high energy particle physics. And the first one is that they reach the highest neutrino energies that we have seen and that we likely will see in the foreseeable future. That means for astrophysics that we are testing the most energetic non-thermal sources in the universe. For particle physics, it means we are testing energy scales that cannot be reached by our own accelerators by several orders of magnitude in energy. And also they travel the longest distances, essentially up to the size of the observable universe. And that means, again, that we're seeing sources from very, very far away as we can see them. And for particle physics, it means that even if we're looking for tiny effects that individually would be very difficult to detect, over a very long distance, many of these effects could accumulate and eventually become observable by the time that the neutrino flux reaches the Earth. And there's one extra not fundamental, but let's say practical reason, motivated, of course, by the fundamental ones, why it's interesting to use these neutrinos. And that is that over the next 10 to 20 years, there's a host of experiments that are being planned or being built today that will target several orders of magnitude across these different sources of neutrinos. And you see some of the ones some of you guys might be working on, like June, Hyper-K, or Juno, at the lowest energies, where we hope to have some synergies between what we do at high neutrino energies with what we do at oscillation energies. And I'll say at least one thing about this later. And at the highest energies, there is a large number of neutrino detectors being planned, either running today or being planned for the next couple of decades. You see here, some of you might already be familiar with IceCube, the largest neutrino detector currently, but there's more of them that are either running today or just stopped running recently. IceCube is the one that discovered neutrinos between TeV and PeV energies about 10 years ago. And today, thanks to it and all the detectors, we are increasing the statistics of those neutrinos. At the highest energies, at the ultra high energies, those neutrinos remain to be discovered. They were predicted in the late 60s by Berezinski, and we hope that the next generation of detectors will finally reach them in the next couple of decades. So that's the both theoretical and experimental landscape that we're gonna be working on. Now, before going into talking about flavor and what we can do with it, let me give you a very simple toy model of neutrino production at these astrophysical sites like the ones I showed a couple of slides ago. And again, please remember, this is just a toy model. Real life is likely very much more complicated than this. But whatever these cosmic accelerators are, and you can think about supermassive black holes or gamma ray bursts or magnetars, they need to hold protons by having an intense magnetic field and slowly but surely accelerate them up to the energies that I said earlier, 10 to the 20, 10 to the 21, which are the highest energies we've seen so far for cosmic rays. But because these acceleration happens in a medium, protons typically will interact with surrounding matter and surrounding photons and eventually give rise to neutrinos. So sources are expected to accelerate protons up to a power law with some spectral index. The lore says it's something like e to the -2, where E is the proton energy. And then there's, for instance, a photon target that is also power law with some peak energy given, say, by a process like synchrotron radiation that may be going on for the electrons that are held inside the source. When these proton and photons, or proton and proton, interact, they give rise to an intermediate resonance, and the resonance decays into either a proton or and a neutral pion, or a neutron and a charged pion. The pions promptly decay, the neutral ones decay into gamma rays, which add to the gamma ray emission from the source that we're looking at, and the charged pions decay into neutrinos, and in particular, 2 mu neutrinos and 1 electron neutrino. And here I am going to forget about the distinction between nu bar and nu, because turns out that experiments that detect these high neutrinos are unable to tell apart neutrinos from antineutrinos. And finally, in the cases where we get a final state neutron, that neutron is no longer confined by the magnetic field of the source, so it leaves and then it beta decays and gives a proton that contributes to the cosmic ray emission that we see. So this network of simple processes relate the energetics of the protons, the photons, and the neutrinos that are emitted by this production mechanism. And roughly the neutrino energy is about 5% of the parent proton energy. So if we see at the Earth a neutrino of 1 PeV in energy, which IceCube has seen, then it was possibly made by a proton of 20 PeV in energy, which we know exists. And these kind of processes happens in sources that are distributed in distance from us, on redshift from us. We don't know exactly what the distribution of the sources are, because we don't know exactly what the sources are. We're just starting to find that out now. But inside them, that network of processes will take place, and they will create TeV to PeV neutrinos. And at the Earth, what we see is the sum of the contribution of all these sources at a detector like IceCube. So currently, actually, we have 3 detectors that are running today that are capable of seeing neutrinos in TeV to PeV in energy. And N3AS, as the successor of N3AS in the Mediterranean Sea, is a little bit smaller than IceCube. Baikal GVD is again the successor of the long-running Baikal experiment in Lake Baikal in Russia, still being built, just like N3AS. And ice cube in the South Pole, which is the biggest among them, is about 1 cubic kilometer of Antarctic ice instrumented with photomultipliers. And when a neutrino comes in, sometimes it will interact with a nucleon in the ice, create a particle shower, and every charged particle in the shower will radiate Cherenkov light, and the Cherenkov light is picked up by the photomultipliers in the ice. So from the properties of the light deposition, ice cube can reconstruct things like the energy, the direction of the incoming neutrino, and the flavor, but that is a difficult thing to do, and I'll show you why in a moment. Very broadly stated, ice cube and the other detectors as well see two kinds of events, at least in the TeV to PeV range. They see either showers, which are made mainly by two of the flavors, nu E and nu tau, and tracks, which are made mainly by one of the flavors, nu mu. They're different, even in this picture. The showers are more or less spherical depositions of light. So a neutrino will have come in from some direction, we don't know. It interacted inside the core of this blob, created a particle shower that is fairly small, like 10 meters or so, and then the light expanded outwards more or less spherically over 100 meters or so. And because it's more or less spherical, the angular resolution of this event is poor. So it's about 10 degrees or even worse, sometimes even 40 degrees. But it's getting better because ice cube people are improving this kind of reconstruction techniques. And then on the other hand, tracks made by nu mu. In this case, a nu mu came in this direction, interacted again somewhere inside this blob, but then out came a final state high energy muon that left a track of light that is more or less easily identifiable apart from the shower that it also originated. And because there's a track, the angular resolution is much better. It's about 1 degree. Now, showers and tracks are more or less easily separable in the sense that we can identify, given an event, if it was one or the other. And because tracks are made by nu mu mostly, then once we see a track, we knew we had a nu mu. But once we see a shower, we don't know if it was a nu E or a nu tau that made it. And it becomes even worse because when I say that it's mainly made by nu E and nu tau, I mean they're mainly made by the charge current interactions of nu E and nu tau with nucleus in the ice. But every flavor of neutrinos, nu E, nu mu, nu tau, can also make a shower by a neutral current interaction. So it's even worse. So a shower, any shower, could have been made by any neutrino flavor. So we try to measure how many nu E and how many nu tau from a sample we get from a sample of detected events. It becomes difficult because of this difficulty concerning showers mainly. Okay, but it's not so dire. Ice cube actually has managed to do this kind of measurements, and I will show later how they look today. But from these kind of events and from the reconstructed energy and reconstructed direction of these events, we can infer 4 high-level neutrino observables: the energy spectrum, how many neutrinos per interval of energy we get, the arousal directions, how many neutrinos from each part of the sky we get, the flavor composition, which is what we care about, and that means what is the proportion of nu E, nu mu, and nu tau in the incoming neutrino flux, and the arrival times. And the arrival times is mainly concerning when we have a flaring astrophysical emission of gamma rays and neutrinos that are possibly coming out of the source at the same time, and we expect them to arrive at the same time also at the Earth. So if we see something different than that, it can tell us about the dynamics of the source or some new physics things. More broadly, again, we have expectations for, I should say, standard expectations for the 4 of them. And when we deviate from those expectations with a reasonable statistical confidence, we could either claim that our original beliefs about how the sources are making neutrinos are wrong or need to be revised, or that there was some new physics involved in it. And I'll come back to this in a moment. But today, after roughly 10 years of ice cube working, one of the main results is that we have knowledge of what is the neutrino spectrum as a function of energy. What you see here is, again, in the x-axis neutrino energy, but now in the y-axis is flux of neutrinos at the Earth. And I'm summing over neutrinos and antineutrinos of all the flavors, multiplied by a couple powers of the energy. You see two lines here. These are power laws, and there are two lines with different gradients because they are based on different data sets collected by IceCube, which have a little bit of difference about what the tilt of the power law is, but they're compatible within one sigma. What you should focus on here is that they reach only about 50 or so 5 or so PeV. We have no data beyond that. And it is with these neutrinos, and especially with the flavor composition of the flux of these neutrinos, that we're going to do all the stuff that I'm going to show in a moment. So let's start delving into that. The big scheme about thinking of flavor oscillations is the following. We have a number of astrophysical sources like the ones I showed earlier. Remember, the neutrinos in the toy model come from the decay of charged pions, which gives 2/3 of the neutrinos as nu mu and 1/3 as nu e. So that's our canonical nominal expectation, I should say. And then neutrinos, as you know, oscillate when they travel. So they don't stay with the same flavor as they were produced with. But by the time they reach Earth, the neutrinos have been redistributed. And again, the nominal expectation is that we expect at the Earth equal amount of nu e, nu mu, and nu tau. And we'll see these things can change depending on both what we produce as the sources and also how neutrinos oscillate as they propagate to the Earth. But instead of talking about absolute numbers of neutrinos, we talk about the ratio of each flavor of neutrino to the total flux. So these F parameters that you see here, and I'm assigning an S here because I'm talking about the sources at the moment. This is what is the fraction of electron neutrinos, mu neutrinos, and tau neutrinos that is emitted by the sources. We know how to calculate neutrino oscillations, in particular how to calculate the probability of a flavor beta going to flavor alpha. This is this P over here. And with that knowledge, we can transform that initial flavor composition into the flavor composition that we expect at the Earth. This is also where there's a possibility of including flavor changing new physics, and I'll come back to that. But before going into that, I want to introduce one tool that you might have seen before, but if not, then this is the ternary diagram that we use, or triangle plot, that we use to plot the flavor composition of neutrinos. And each axis corresponds to one flavor, electron, muon, and tau. And each point inside has coordinates that added together always yield exactly 1. So for instance, every corner corresponds to a pure flavor. And if we put, for instance, one point over here, and we want to know what is the nu e fraction of that point, we just follow the tilt mark corresponding to the nu e flavor, and that's 20%, or the tilt mark corresponding to the mu flavor, and that's 60%, and the remaining tau flavor has to be 20%, so it always add up to 1. And in the center of the triangle, for instance, you get equal amount of each flavor, so it's 1/3, 1/3, 1/3. Always we show first nu e, then nu mu, and nu tau, so that you keep track of that. And then we show not just points, but regions inside a triangle. Okay, so coming back to the big picture, we have sources producing neutrinos with some initial flavor composition, and then oscillations transforming that flavor composition along the way. The flavor oscillations depend on, in particular for high energy astrophysical neutrinos, 4 oscillation parameters: 3 mixing angles, theta 1, 2, 2, 3, and 1, 3, and 1 delta CP violation phase. And those are known experimentally to within different degrees of uncertainty. But for now, let's ignore the uncertainty and let's assume that we know them perfectly well from fixed to global oscillation data. So let's take our toy model of production of neutrinos, where we produce neutrinos by a decay of pions. So that gives us 2 mu neutrinos per each electron neutrino. Let's call that the full pion decay chain. And that means that we have 1/3 of nu e, 2/3 of nu e, and 0 nu tau. We put that in the axis where it corresponds, because this is an axis where there's zero tau content. And then we turn on oscillations, and assuming that we know perfectly well the neutrino mixing parameters, that takes us to the center of the triangle, which is, as I said, the nominal expectation that we have, equal amount of each flavor at the Earth. In some sources, we might have intense magnetic fields that cool these muons, the intermediate muons, before they have a chance to decay, and therefore the neutrinos that they decay into are no longer high energy. And so the only high energy neutrino we have is these new mu that comes directly from the pion decay. In those cases, the muon damped cases, the initial flavor composition is purely new mu, and then we turn on oscillations and we end up close to the center but off to the left, so smaller nu E content. And another benchmark that we typically use is neutrinos coming from the beta decay of neutrons or neutron-rich isotopes, and that puts us initially in the corner here of pure nu E bar composition, and then at the Earth off to the center, off to the right, to the center. So a high nu E fraction. Now, you might ask if these are the only three possibilities, and definitely not. This we use just as benchmarks. You can have mixtures of the different compositions in between these, and you can also have them change as a function of energy as some processes become available at different energies. And we'll come back to that, and I'll show you how this varies. But okay, let's keep this as benchmarks, and then let's now switch to the thing that I said was difficult to do, which is measure flavor composition. So remember, it's difficult because showers, we don't know what flavor made them. But regardless of that difficulty, IceCube has been successful in measuring the flavor composition. So again, we have our three benchmarks here from our theoretical predictions. And the first measurement of the flavor composition by IceCube was in 2015. And it favored a best fit of the flavor composition without any tau content. So best fit here is on the axis. And you can tell that it's a difficult measurement because a few years later, they repeated the measurement with a different data set and different techniques. And then the best fit moved to the opposite side of the triangle when there's no nu E content. And most recently, the measurement was improved by including signatures or events that are clean events for finding high energy new taus, so-called double banks. And with those included, the latest measurement is actually moving towards the center of the triangle, which is, as I said, our nominal expectation of equal flavor distribution at the Earth. Still, it is very clear that the measurement is still difficult because the containment region is huge. So when we claim something about the flavor measurement of the neutrinos at the Earth, it is done with a large uncertainty so far, but it will be hopefully better, and I'll show you how much better in the next few years. Now this is about measurements, but let's come back to one of the assumptions that we made earlier, which is that we know these oscillation parameters perfectly well, which is of course not true. These are constants of nature that we measure with some uncertainty. And if we take into account that uncertainty, then our benchmarks, which were just points so far, become regions. And the size of the regions, which is here represented by the differently shaded regions, they reflect the size of the uncertainties on the mixing parameters. On the theta12, theta23, theta13, and delta CP. Most importantly, on the first two, theta12 and theta23. And here a problem becomes apparent. And the problem is if we project, let's take these two, the red and the orange regions. If we project their flavor composition onto just one of the axes, let's say the nu mu axis to the right, then it is clear that there's a big overlap between the two theoretical predictions. And that means that even if we had a very good uncertainty with which to measure the flavor composition at the Earth, our theoretical predictions themselves are not unique and able to separate the two different production mechanisms, the full pion decay chain and the muon damped decay chain. So And the same happens, for instance, if we project things to the new tau axis, especially for the orange and the red regions. And so that means that it's not only a matter of improving our flavor measurements in things like IceCube, but also a matter of improving our knowledge of the mixing parameters. The situation is a bit worse because, as I said earlier, these are just benchmarks, and we could really be making neutrinos not just by these three production mechanisms, but by anything in between. And if we do that, if we account for that and also account for the uncertainties in the mixing parameters, then we end up in this blue region, bow tie-like region, where we need to be at the Earth if oscillations are behaving the way we believe standard oscillations behave. So said differently, and this should be actually quite promising, said differently, this is the small region where if oscillations behave in the standard way, we need to measure the flavor composition at the Earth. If the flavor oscillations do not behave in the standard way, but rather there's some new physics in it, and if we make a measurement of that outside the blue region with sufficient precision, then that means that we have discovered some new physics. The fact that this is a small region compared to the full triangle, like about, let's say, 10% of the full triangle, means that most of the triangle is reachable only with new physics, which is promising prospects for testing, constraining, or discovering new physics in the flavor composition. Okay. So what can we do today? Let's see. I'm gonna put three test cases for what we can do more or less today with the measurement of flavor composition. One of them will be about astrophysics, and the other two will be about fundamental physics. And then I'll show what we can do in the near future. And the first one then is astrophysics. And again, let's look at our point model of neutrino production. In sources that have strong magnetic fields, the charged particles that are here, the protons and the pions and the muons, may cool by synchrotron radiation. And the cooling is manifested, of course, it depends on the size of the magnetic field. It also depends on the other properties of the sources, like the size of the source and also the speed with which the production region is moving, so the both Lorentz factor. But if such a cooling exists, then it manifests as kinks in the power law behavior of the diffuse neutrino flux that is made by the sources. And so we can look for these kinks, and by finding them or not finding them, we can put limits or discover the value of the magnetic field that the sources are harboring. So to make that concrete, let's look at this. The neutrino energy again is in the x-axis, and the flux is in the y-axis, again multiplied by 2 powers of the energy. And I've separated the flux into nu E, nu mu, and nu tau, and given 2 examples. One where all of the sources in the population of sources, which is distributed in redshift, is containing 30 kilogauss magnetic field, and the other where it is containing, every source is containing 300 kilogauss magnetic field. Let's focus on the dashed lines. You see, instead of just having a simple power law with no features, you see that it at some energy acquires a kink in the spectrum. The first one at low energies is due to the cooling of the muons. So the muons cool before the decay, and remember then that means that we only get the high energy nu mu from the direct pion decay. And then at even higher energies, the pions themselves cool, and then we get a second kink over here. And at even higher energies, which are not featured here in the range of energies, the protons themselves cool, the protons that give rise to the pions that eventually decay into neutrinos. So if we then crank up the magnetic field from 30 to 300 kilogauss, then those kinks appeared at higher energies. So what we can do is compare predictions for the diffuse neutrino flux with the effects of synchrotron cooling in them versus the data of IceCube. And in this case, I used a couple of data sets. The flavor bit comes here because every kink is associated to a change in the flavor, and that's what you see in the bottom panel here. So we use both the shape of the spectrum and the change in the spectrum and the change in the flavor composition of the diffuse flux to constrain the value of the magnetic field that is introducing these changes. And if we do that using those two data sets that I'm putting in here, then we find no evidence of this kind of kinks, but we can put limits on the population average magnetic field intensity. And that's what we did. So what you see here is in the y-axis is the magnetic field in the rest frame of the sources. And in the x-axis is the Lorentz factor of the production region of the neutrinos inside the sources. So the dashed region over here at the top is the one that is disfavored by the non-observation of those spectral kinks and changes in the flavor composition that I was talking about. And that's overlaid on the approximate regions where different candidate sources could be that could be making neutrinos. The constraints that we're putting, I should say, are disfavoring a little bit of the parameter space of possible sources of neutrinos that may be harboring intense magnetic fields. And in particular, that is low luminosity GRBs and a little bit of high luminosity GRBs. Many of the candidate sources of neutrinos, unfortunately, have weaker magnetic fields in them, and we are not able to constrain them with the current data. So all the candidates are not constrained by looking for these kinks. But that's what we can do with flavor today for astrophysics, at least one application. There are more applications actually in testing fundamental physics. And the way I always like to organize this for fundamental physics is to lay out some of my favorite new physics or new neutrino models at high energies. And some of them will act at production, so at the sources. Many of them will act during the propagation from the sources to the Earth, and some of them will act at detection, so inside the Earth or inside the detectors themselves. And they will affect one or more of these high-energy neutrino observables that I introduced earlier. And in particular, what we're going to look at is the bottom right corner. By the way, I'm not going to talk about all of these. I'm going to just focus on a few of them, but I'm going to talk about the few of them that affect flavor composition. Before singling out 2 or 3 models that could do that and showing what constraints we can put today using flavor, let me quickly flash some of the effects of these different neutrino models on the flavor composition. For instance, we could have neutrino decay, and I'll come back to this one in particular later, which changes the flavor composition of the neutrinos at the Earth. We can test the unitarity of neutrinos at high energies, so whether neutrinos are only changing between the 3 active flavors or they're leaking out into a bigger system. We can test the Lorentz sensitivity and variance of the neutrino sector, and I'll come back to that as well later. We can test non-standard interactions of neutrinos inside the Earth, and the mixing of active and external neutrinos, and new interactions between neutrinos and electrons or neutrons and protons. So rather than going through each and every one of these, I'll focus on 2 cases. And first is Lorentz invariance violation tested via the flavor composition. So the picture that you need to have here is that if Lorentz invariance is violated, it might be violated by there being a fundamental tensor field that is with some specific direction in the universe, let's say, and then that is coupling with the neutrinos, and by doing so, it is effectively introducing a new term into the Hamiltonian that drives neutrino oscillations. So for those of you, let me get a bit technical for a moment. For those of you that work on neutrino oscillations, the term in blue here is the standard oscillation term. It depends on the 3 mixing parameters I was talking about earlier, which are hidden inside this mixing matrix. and two mass square differences of the neutrino mass eigenstates. The new physics terms, or the Lorentz invariance violating term that are being introduced here, have approximately the same shape, but a different energy dependence. Instead of being 1 over E, is E to some power, suppressed by the energy scale where those effects take place. So this could be a large number, like a Planck mass or so. And it's a tower of these different operators. So it could be different contributions for different dimension operators. Regardless what happens when one adds this extra term into total Hamiltonian, given that we have no handle on the size of the elements of this new mixing matrix and these new these new eigenstates here, then they can vary more or less wildly, and we can use data to put limits on them. So as prediction, for instance, if we start from, let's say, this corner, sorry, this part over here, remember we start with 1/3, 2/3 zero at the sources, we can get anywhere inside this yellow region rather than just being close to the center. If we start now from a pure new mu composition, then the new Lorentz violating term means that we can be anywhere inside this red region, and the same goes for different assumptions of where we start. So we're not confined anymore to being close to the center of a triangle, but we can actually be anywhere in a triangle. And because the deviations then are large compared to the standard expectation, then it turns out we can put pretty strong limits on the size of the couplings that control these deviations. And that is exactly what IceCube did a few years ago. So just as an example, it took one of those coefficients that related to the Lorentz invariance violation. This is the alpha beta coefficient for a 5-dimensional operator. And what you see here is the limit using real data as a function of the initial composition of the flavor composition of the sources. And let me skip the details about exactly what the shape is telling us, but what is important here is that using IceCube data, which is between TeV and PeV, we can improve over the atmospheric limits, which is here the shaded region, by several orders of magnitude. And that is because for a 5-dimensional operator, which is the one in this particular plot, the energy dependence of the extra terms in the oscillation goes as E squared. And because we have a big difference between atmospheric energies of GeV and astrophysical energies of 100 TeV, then that means that we can improve the limits by several orders of magnitude. And that's what we see here. In fact, today, the tightest limits on this kind of Lorentz invariance violating couplings come from these flavor measurements at IceCube. And they will probably get better in the next few years as more data come. So this is what you can do for testing fundamental symmetries with flavor. We can also test whether neutrinos decay or not. And again, we start from some initial flavor composition, just let's say equal amount of new. Now I'm not starting from an equal amount of new E, new mu, new tau, but I'm positing that there is equal amount of each one of the mass eigenstates. Remember, the neutrino of some given flavor is a superposition of different mass eigenstates. So if we start with some proportion of each mass eigenstate, and we allow the heavier ones to decay into the lightest one along the way to the Earth, then we expect a different flavor composition from the standard one at the Earth. And the way this is calculated is by this kind of flux attenuation. So the flux of the neutrino mass eigenstate I is attenuated by an exponential factor that depends on the distance it travels. It is less intense, the decay, for neutrinos of lower energy because the boost is less intense. And it depends on the mass of the mass eigenstate that decays, on the lifetime of the mass eigenstate that decays. And in particular, this m over tau ratio, or tau over m, actually, which I will show later, is not something that we can break. So we always put limits on tau or m, not on m or tau separately, which is what we say here. So again, lower energy neutrinos are longer lived, and neutrinos that travel longer distances are more attenuated. That's what the exponential is doing. So for high energy cosmic neutrinos, what we have is, again, I put sources that are making some proportion of different mass eigenstates initially. If neutrinos decay in this way, so if the heavier ones are nu2 and nu3 and the lightest one is nu1, let's say in a normal mass ordering picture, then if the neutrinos have completely decayed by the time they reach Earth, then we'll expect nu1 at the Earth. Conversely, if nu1 and nu2 are the most the heavier ones and nu3 is the lightest one, then we expect mostly nu3 at the Earth if they have decayed completely along the way. So we can actually contrast that expectation with the data. And here the key aspect is, I'm of course foregoing the details about the decay possibly being incomplete and whether the neutrinos are detectable or not after the decay. But here, the main aspect that we want to focus on is the fact that each one of these mass eigenstates, nu1, nu2, and nu3, have a different flavor content. So in fact, that's more or less how we define them. So nu1 is the mass eigenstate that has the most nu content. And of course, there's a region because that content depends on the values of the mixing parameters. So it's not just a point, but there's an uncertainty to it. And nu3 is the one that has the least nu content. And all of them have about the same amount of nu and nu tau in them. So given that we know what is the expectation for decay in those two scenarios, we can contrast that against the data. In the case of nu1 being the lightest one and the one that the heavier one decays to, then we expect something for the flavor composition that looks like the flavor composition of nu1 at the Earth, because that's the only remaining eigenstate. In the case of the inverted mass ordering, where nu3 is the lightest one, then we expect that the flavor composition at the Earth is given by the nu3 mass eigenstate instead. And if we look at the data, and please look at the dashed dotted line here, which is the 2015 measurement, so on real data by IceCube, then this blue bit over here, which corresponds to a nu1 flavor composition, is the one that is at least partially disfavored at the data, is outside the 99.7% confidence interval of the flavor measurement. So this one is disfavored, and because that's disfavored, we can put a lower limit on the ratio of the lifetime to the mass of the nu2 and nu3 eigenstates. And we need a couple of ingredients, which I'm not going to go into details with. The first one is we need to know the distribution of the mixing parameters, which control the oscillations, because that also determines the flavor composition of the nu1 eigenstate that we're trying to compare against data. And the second one is how well we can measure the flavor composition inside a triangle. That is something that IceCube can give us. So when we put all of those together, we put a limit on the neutrino lifetime as a function of the neutrino mass. And the present day one coming from this kind of flavor measurements is the one in the lightest blue over here. And in the future, once the measurements become better, as you see, these ellipses are showing how the flavor measurements could improve in time. If that happens, then we will get improvement on the upper limit, on the lower limit, sorry, of several orders of magnitude in the next 3 years. Okay, so this is more or less what we can do today with flavor composition measurements. Let me just move on. Okay, but we will be able, hopefully, to do better in the next couple of decades. And the first improvement is high statistics, and that is mainly going to happen because there's more detectors being built today. So together with IceCube, N3AS, and Baikal GVD, there's hopefully going to be P1 in Canada, Trident in China, Trinity in somewhere in the US, and Tambo maybe, which is a new tau detector in Peru. So what we had so far, remember, is something like this for the flavor measurements. In the future, then together, if we put together all of these detectors, which again, it's a big ask, but it's something that is within the realm of possibilities, then the flavor composition measurements could improve, like you see here, with 8 years of data. This is actually just with IceCube, assuming that in 2020 we had put together all the data that we could and made a flavor measurement analysis. You maybe could have gotten something like the light blue region over here, which is an improvement of about a factor of 5 over the purple one, which is based on actual data, but not using the full data set. And in the future, using Ice Cube Gen 2, which is about 8 times the size of Ice Cube, we could improve that by a factor of 2 or so more. And further projections using old telescopes really pin down the measurement of the flavor measurements to within a few percent in some directions. So this is the darkest blue that you see over here. But of course, these are projections for the 2040s or so, and depend on the fact that there's going to be more than one big neutrino detector working at that time. Okay, so that's again for the flavor measurement projections. Let's think about what the theory projections look like for the next few years. And that is where the synergies with the lower energy experiments come in that I mentioned at the beginning. So just imagine we have some flavor region at the Earth. I'm just drawing a square here. If we measure theta to 3 better, one of the mixing parameters, then that flattens out the square along the new tau direction. If we measure the theta 1,2 angle better, it squishes it in the new E directions. If we measure those two together better, then that reduces the size of the flavor composition region at the Earth. And that is exactly what's going to happen in the next few years. So currently our predictions for the flavor composition of the Earth look like what I showed earlier. This is 2020 with the current knowledge of the mixing parameters for my global oscillation fit. In the next few years, Hyper-K will come online and measure theta to 3 better. So it will squish things along the new tau direction. Juno will squish things along the 1,2 direction, sorry, the new E direction. And then together by the year 2030 or so, they will make the regions that we have now become more or less points. And there's extra marginal improvement all the way to 2040, and of course also by June. So at that point, we have both a precise measurement of the flavor composition in the neutrino telescopes, but also a precise theoretical predictions of the standard oscillation regions expected based on the knowledge of the mixing parameters. Okay, so what can we do at that point? We can start asking the really hard questions, like going back to finding out what happened at the neutrino sources. So far, we have been going in this diagram from left to right. We have made an informed guess about how neutrinos are being made in the sources. We have used our knowledge of the oscillations along the way and calculated what is the expectation for the flavor composition at the Earth. But now we want to do the reverse. We want to measure something at the Earth for the flavor composition, use the knowledge of the oscillations that we have, which is going to become better as I showed you, and then infer what the flavor composition was at the time of production inside the sources. We can already do that today, actually, but it's not as good as we'll get. So there's 2 ingredients involved in that. The first one is the flavor composition measurement at the sources, sorry, at the Earth. And the second one, as I said, is the knowledge of the flavor of the oscillation parameters. And this is just an example of how it could look like for June for 2 of these parameters, delta CP and theta to 3. So we put those together, you know, you need to know what the likelihood is across the full triangle. That's why I showed this. And you make a Bayesian analysis, then you can start inferring what the flavor composition is at the Earth. So what I'll show on the left is a potential flavor measurement at the Earth. And on the right, I'm going to show you what that entails about the inferred flavor composition of the new E flavor only at the sources. So if we start with today's knowledge of the flavor composition at the Earth, then it turns out that what we infer at the sources is actually preferring something that makes mostly new mu. So no new E content, only new mu production. I'm assuming that there's no new tau production here at the sources. Now, if we make projections about how these measurements of the Earth could look like, the darker blue here, we repeat the process, then we start favoring what we expect, like that's the nominal expectation, a neutrino production by pion decay. And if we make that ellipse tighter and tighter as more neutrino telescopes come online and better measurements of the oscillation parameters become available, then eventually we can get to a precision of the measurement of the flavor composition at the sources within percent level. And in that scenario, we can start testing competing models of neutrino production, which is what we want to do eventually. This allows us also to measure the flavor composition as a function of energy. And this is especially interesting because it allows us to see changes between our benchmark scenarios. So as I said, these are just 3 benchmark points, but things can run through between them at different energies as different processes become available or turn off. So that's exactly what we try to do here. Let's just put a very simple example, where we have a power law that at some energy it has a kink, and that kink is alike the one we expect when the intermediate muons cool by synchrotron radiation. So at that energy, the flavor composition changes from having 1/3 of nu e, 2/3 of nu mu, and 0 nu tau, into having 0 nu e, complete nu mu, and no nu tau. So something like you see here on the left. So at some energy, in this particular plot is at 1 PeV, things change and introduce a kink where the flavor composition changes. We allowed the energy at which this transition happens to float in a comparison to present day data. And what we find is that there is no sensitivity to there being such a kink in the spectrum or such a change in the flavor composition. There is a preferred value for that transition, is about 200 TeV, but you can see that the flavor composition at low energies, so below 200 TeV, and at high energies, so above 200 TeV, are essentially on top of each other. So there's no sensitivity to distinguishing between them. In the future, however, again, putting together more than one detector, actually many of them, and including other data sets, the separation between the high energy and the low energy regions gets a lot better. But that's a very difficult measurement. As you can see, the 68% containment regions are touching. So making a separation of more than 1 sigma is going to be hard. It becomes a little bit better if the transition happens at lower energies, because that means we have more data in the high energy bin, which allows us to identify transitions better, but still is a difficult measurement. So it might take us a few, maybe even a decade or so, to start making claims that are strong regarding the flavor transitions in the high energies. And again, it depends on where the transition happens. Okay, so in the interest of time, and because as I said, I was going to be slow, let me actually jump ahead and show you one final bit, which has to do not exactly with high statistics, but with high energy. So let me go into that. Oops, that's not what I wanted to show you. Give me a second. Yes, okay. So so far, let me need to go back for a second. So far, what I have been talking about is oops, give me one moment. Yeah, okay, there we go. So far, I've been talking about these neutrinos that reach up to PeV energies. There's more neutrinos that we expect there to be at even high energies, and there's detectors that are targeting them over the next 10 or 20 years. The question is, can we do flavor measurements with those? And it is a non-trivial question to answer, because these are no longer optical detectors. These are, most of them, radio detectors, and the signals between different flavors are even less distinguishable than in optical detectors. So we try to answer the question whether there's actually any flavor sensitivity at those energies. And this is further complicated by the fact that we don't have a flux at those energies. We only have predictions, and the predictions are, and I'm gonna just flash them, are, well, all over the place. And because of that, then we need to more or less make predictions for a number of different processes. So a number of different flux assumptions, sorry. I'm gonna show you quickly what that looks like. Sorry that my computer is a bit slow. I think it's loading the pictures. There you go. So just to flash how these things look, I said we don't have a flux that is measured at those energies, but we have many predictions. And the fact that you see many curves at those high energies means that we need to account for the possibility that we either see many neutrinos when the flux is very high at 100 PeV or more, or essentially see no neutrinos. And it's in between where, of course, we have the sensitivity to measure something. Fortunately, many of these models are discoverable within a few years, but the question is whether we can have or not sensitivity to the flavor. And it turns out that it might be possible, but it is tricky. So what we found, let me skip what I've wanted to show first. I'll show directly what I wanted to show to talk about radio here. What we found is that radio has some sensitivity to distinguish between flavors, and that is because new muons and new taus actually make final state muons and taus that are energetic enough to trigger many radio showers in the eyes that these detectors can pick up. So when you see events that contain more than one radio burst, which is the equivalent to the optical Cherenkov radiation, then that is an event that was likely due to new muon new tau. And when one sees, so that gives us its sensitivity to new muon new tau. And when one sees new events, whose radio emission contains wiggles at the very end of the emission, that is due possibly to new E's interacting, because new E's and create a final state electron that is energetic enough that they undergo Landau Pomeranchuk-Migdal effects, which means that the final state electron will have its cross-section with the medium decreased. And as a result, the showers and the radio emission from the showers that they create is elongated in time. So when sees a waveform that is longer than you expect, then that might be due to new E. So putting together the sensitivity of new mu and new tau and the sensitivity to new E, one can make a measurement of flavor composition that looks like more or less like this for some flux prediction. So now we're talking about energies of 100 PeV, no longer PeV energies. And it's for the first time it becomes possible, perhaps, to make a measurement of the ultra high energy flavor composition and then extend the flavor composition measurement that we can do today to even higher energies. So again, depending on what the initial flavor composition is, we will end up somewhere else, but it's still in the works. And of course, it will depend on the size of the flux that we eventually have. Okay, so I hope I gave you a big survey of the state of flavor composition at high energies. The gist of this is that we need to build bigger. Otherwise, we don't get statistics at TeV to PeV energies. We need to build different. Otherwise, we don't get to the ultra high energies. We need radio detection as opposed to optical detection, which is still in development at large scales. And as I showed you, most of the predictions depend on there being more than one detector to increase statistics. And that means that we need to work together. So I think this is all within possibilities for the next 20 years or so. But it's also up to you guys to figure this out. So thank you very much.
Thanks, Mauricio, for this very nice talk.
And I apologize. I told Anupam earlier I have a fever, so if I went a bit over, it's because I'm a bit slow today. So
no, it's fine. Yeah, I think time-wise you have done great. So, are there any questions for Mauricio? Yes, there is a question from Julian. Julian, can you please unmute yourself?
Yeah, thank you very much. It was very interesting talk. When you talked about the decay of starting from massive states and looking at decay, you basically assumed, if I'm correct, that there will be always like a total decay into the lightest mass state. So I guess in this case, basically you showed as an example it would be equal numbers of all the three states. I guess we don't care. Basically, everything will go into the lightest state. Have you looked at like other assumptions depending on the scale of these decay rates and all that?
Yes, no, that's a good question. So I just showed the easy case, but of course, if you have some of the unstable neutrinos surviving into the Earth, then the prediction is less clear, right? Because you know you no longer have just a new 1 or new 3 flavor composition, but you have some mixture of the flavor composition of the new 1 and new 3, which depends on the lifetime of the unstable neutrinos. And yes, we looked at that. So when we make this lower limits, sorry, on the lifetime, we actually allow for that possibility. So we don't assume that the decay is complete. For the purpose of what I showed, we did assume that the 1 decay channel is that new 2 and new 3 decay into new 1, which is not the only possibility. You could have new 2 decaying into new 3, for instance, or new 3 decaying into new 2, and then into new 1, so that you can play around with that. And those limits also exist. So this has been tested.
Okay, thanks.
Yep.
Baha, can you please unmute
Well,
yourself?
Yeah, thank you. Very nice talk. Very nice summary of quite a lot of research. If you mentioned that, I missed that. If you have 1 or more subtle neutrinos, would that change the results significantly?
That's a good question. Let me go back to that slide. And the answer is no, but the qualified answer is no, because of the very strong limits between active and sterile neutrino mixing today. So let me actually show you the picture I want to show you. So let's say if you didn't know about limits on theta 1,4 or any of the other mixing between active and sterile, then in principle, there you go. In principle, you could allow those mixing angles to vary to whatever value they could have. And then you could have large deviations in the flavor composition expected at the Earth. So you could end up being in one of the sides of the triangle where you cannot reach with standard oscillations. But given that those mixing angles are now pretty strongly constrained, the allowed deviations are pretty small. And the only caveat of that is that if you have a source which by whatever mechanism, I don't know which one would be, can produce sterile neutrinos directly, then you could have at the Earth a large deviations from the standard flavor oscillation, but for the composition, sorry. But I don't know how an astrophysical source could make sterile neutrinos directly.
Okay. Thank you.
Yep.
Okay, I guess there are no further questions, and so I think it was a very nice talk. And thank you, Mauricio, for accepting the invitation and giving the seminar here. Okay, I will see you everyone in the next week then. Thank you.
Thank you. Bye-bye.
Thank you.
Bye.